Why does some ink disappear and then reappear like magic? That is the mystery behind the disappearing ink paradox, where certain chemical reactions seem to defy permanence by reversing themselves invisibly. You might have seen this in novelty pens or spy kits. You write a message and it vanishes after a few seconds or minutes. But what's really happening? These are reversible chemical reactions where the product, the ink color, breaks down or changes form due to environmental triggers like air, heat, pH, or light without any visible trace of the process. It's not magic, it's chemistry playing hide and seek. So how can a reaction be reversible without leaving a trace? Some molecules are designed to be pH-centered or thermochromic, meaning they change structure and color under certain conditions and then quietly revert back. Example, thymolphthalin, a compound used in disappearing ink, turns blue in basic conditions, but becomes colorless as the solution becomes neutral over time. Analogy. It's like a mood ring for molecules. What you see depends entirely on the environment, and the change can vanish without warning. The paradox lies in how seemingly permanent changes can reverse silently, revealing how fragile and dynamic chemical states really are. How can inks that leave clear-colored marks suddenly vanish, only to reappear later under heat, light, or a simple pH shift? Disappearing inks exploit reversible chemical reactions, often Leuco dyes, or pH sunset indicators, that transition between colored and colorless forms without any visible residue, creating the illusion of vanishing writing. So far, so good, until we delve into the subtle equilibrium that governs these transformations. The disappearing ink paradox arises when a solution that once yielded a vivid hue shifts invisibly back to its original colorless state, despite no apparent external removal of pigment. In theory, the ink's dye molecules simply toggle between two structural forms, one conjugated, colored, and one non-conjugated, colorless. Yet in practice, maintaining a stable, reversible balance between these forms without degrading the paper or leaving ghost images demands an exquisite control of reaction kinetics and environmental conditions. At its core, most disappearing inks rely on Leuco dyes, molecules that can reversibly gain or lose electrons, redox chemistry, or protons, acid-base chemistry. In their colored form, the dye's extended p-electron system absorbs visible light. In the Leuco form, that conjugation is interrupted, rendering the molecule transparent. A slight change in pH or exposure to an oxidizing agent can push the equilibrium toward one state or the other. Crucially, these reactions must be fast enough to appear instantaneous, yet gentle enough to avoid side reactions that would permanently stain or damage the substrate. Yet even such clever designs are vulnerable when scrutinized on a molecular level. Thermal fluctuations, moisture in the air, or residual acids on paper can slowly drive the dye off its intended course, causing partial coloration, yellowing, or incomplete disappearance. And when a hidden oxidant like ozone in sunlight or a drop of weak acid, lemon juice, is applied, the equilibrium shifts back, triggering the dye's return as if by magic. The paradox lies in the fact that nothing is truly erased. The molecules remain, patiently awaiting the right trigger to reveal themselves. At even finer scales, the interplay between solvent evaporation, substrate porosity, and molecular mobility can create unexpected memory effects. A section of text might reappear only under UV light, where photons provide the energy to overcome activation barriers, or under gentle heating that accelerates proton transfer. These non-intuitive pathways remind us that chemical systems are rarely at perfect equilibrium and that tiny environmental perturbations can yield dramatic reversible changes in appearance. In essence, the disappearing ink paradox underscores the dynamic nature of chemical equilibria. What seems permanently gone is merely lurking in an invisible form, ready to be coaxed back into view. It challenges our expectation that a mark either stays or fades for good, revealing instead a world where molecular reversibility and the delicate balance of competing reactions can play tricks on our senses, much like the deeper paradoxes that test the limits of physics and engineering. The disappearing ink paradox refers to chemical reactions in which a visible change, often color or opacity, spontaneously reverses without leaving any obvious trace. These reactions appear to erase their own evidence, returning to the initial state as if nothing had occurred. This contradicts the common assumption that reversing a reaction must produce a detectable change equal in magnitude to the forward process. The paradox underscores how macroscopic disappearance can mask complex underlying molecular dynamics. Leuco dyes used in thermal printer paper turn colored when heated, but revert to colorless as they cool, making the print vanish. It is like writing with invisible ink that briefly appears under heat and then fades away, leaving the paper indistinguishable from its original form. Classical chemistry teaches that reversible reactions should proceed forward and backward in a manner detectable by concentration changes or equilibrium shifts. In the disappearing ink paradox, however, the backward reaction restores the original appearance so completely that no visual cue remains. This phenomenon reveals that not all reaction progress can be monitored by eye or simple colorimetric methods. It challenges the notion that chemical reversibility is always accompanied by observable macroscopic signals. Solutions of pH indicators can change color upon acid-base titration and then revert to the original hue when the pH is readjusted, hiding the titration history. It is like a reversible mood ring that shifts color with temperature, but then resets perfectly when cooled, concealing its prior state. At the molecular level, reversible reactions reach a dynamic equilibrium where forward and backward reaction rates are equal. When equilibrium heavily favors one side, the net change becomes imperceptible, even though individual molecules continue to react. This balance creates a steady-state appearance, masking the constant microscopic turnover. The paradox arises because visible changes depend on concentration thresholds that may never be crossed in the reverse direction. In starch-iodine complexes, the deep blue color disappears when iodine dissociates, yet the molecular exchange continues unseen. It is like a busy intersection where cars continuously pass, but the traffic flow looks steady, hiding the constant motion. Catalysts can accelerate both forward and reverse reactions without being consumed, promoting an invisible return to the starting material. Short-lived intermediates may accumulate just enough to produce a transient color before being rapidly converted back. When the intermediate's concentration falls below the detection limit, the reaction appears to have vanished. These mechanisms demonstrate how the presence or absence of detectable species dictates our perception of reversibility. In some enzyme-catalyzed reactions, colored intermediate substrates form briefly and then convert back so quickly that the color flash is nearly undetectable. It is like a flash mob that assembles for a split second and disperses before anyone realizes it happened. Thermodynamic favorability determines the equilibrium position, but small energy differences can render reverse reactions virtually invisible. When the free energy change is close to zero, the system flits between states with minimal net change in observable properties. Visual cues rely on crossing energy barriers large enough to create detectable intermediate populations. In the paradox, these barriers are tuned so that the reverse transition leaves no macroscopic footprint. The reversible oxidation of certain metal complexes shows color only when the oxidation state briefly accumulates, but then reverts so completely that the solution looks unchanged. It is like a light breeze stirring leaves momentarily, then dropping so gently that the forest floor appears undisturbed. Nonlinear kinetics can produce sudden on-off behavior where reaction progress is only visible beyond a threshold. Below this threshold, the reaction proceeds but remains invisible to our senses. Once the threshold is crossed in reverse, the disappearance happens seamlessly without intermediate shades. This threshold-dependent visibility is central to the paradox of seemingly reversible yet undetectable reactions. Certain photogrammic compounds change color only above a light intensity threshold and revert below it without showing intermediate hues. It is like a digital display that only registers values when they exceed a set limit, otherwise appearing blank. The disappearing ink paradox informs the design of tamper-evident inks and reversible sensors that hide or reveal information under controlled conditions. Understanding invisible reversals allows chemists to create systems that respond predictably to external triggers and then mask their own history. This has applications in anti-counterfeiting, secure communications, and resetting diagnostic assays. It highlights the need for analytical methods beyond simple visual inspection. Security inks that fluoresce under UV light only during inspection and then revert to invisibility protect against document forgery. It is like a confidential message that appears under a special light and then vanishes, ensuring no trace remains. Capturing invisible reaction reversals demands sensitive spectroscopic or chromatographic techniques capable of tracking transient species. Standard colorimetric or visual observations can miss the continuous microscopic turnover. Modeling these systems requires integrating kinetics, thermodynamics, and detection limits to predict when reversals become undetectable. These complexities make it challenging to fully characterize seemingly disappearing reactions. Time-resolved spectroscopy may reveal fleeting absorption peaks that correlate with intermediate species otherwise invisible in steady-state measurements. It is like using a high-speed camera to catch a hummingbird's wings in motion, which appear still to the naked eye. Advances in real-time molecular imaging and ultra-sensitive detectors promise to illuminate the hidden dynamics of disappearing reactions. Integrating machine learning with kinetic modeling could predict conditions under which reversals become invisible. These developments will enhance our ability to design reversible systems with tailored visibility for technological and scientific applications. Ultimately, resolving the disappearing ink paradox deepens our understanding of how perception interacts with underlying chemical reality. Single-molecule fluorescence microscopy is being used to track reversible binding events that escape ensemble-level detection. It is like upgrading from binoculars to a telescope, revealing details of celestial motions that once seemed to vanish into the night sky.